tornado. The dictionary describes it as a small, violent storm or an outburst of applause. Both are more apt than those who gave the Panavia tornado its name could ever have guessed. Since it first went into combat in January 1991 in the appropriately named Operation Desert Storm, the tornado has won many devotees. The end product of the greatest multinational weapons development program in history, the tornado has emerged, despite pessimism from many quarters, as one of the finest of all modern multi-role combat aircraft flying anywhere. Disregarding predictions that it would be a jack of all trades but master of none, the tornado has instead proved that you can be a master of all trades. Designed to meet the exacting requirements of 3 of the world's most professional air forces plus a navy, it packs a punch much greater than that of many other aircraft, both larger and more costly. The story of how this was achieved goes back many years. Tactical aerial combat really began during the First World War. Initially, aircraft called Scouts were used for reconnaissance and artillery observation duties. Then some crews started using small arms to shoot at each other, or carrying grenades to drop on troops on the ground. From these primitive beginnings emerged the concept of the fighter and the bomber. One was designed with speed and agility in mind, the other with range and load carrying. It would be a long time before the multi-role concept could be brought into being. During the Second World War, the Spitfire emerged as the epitome of the fighter. With beautiful lines and handling qualities, as well as a powerful battery of forward-firing guns, it could equally well shoot down enemy bombers or dogfight with their escorts. By the 1960s, most people regarded the fighter purely as an interceptor and the bomber as just a bomber. An inevitable consequence was aircraft like the Royal Air Force's Lightning. These sleek machines were almost all engine, and in terms of brute power have few rivals even today. No one could forget that vertical climb almost as soon as the wheels had left the runway. But the aircraft had very limited endurance and payload capacity. They could not carry out ground attack or reconnaissance missions. To combine such capabilities in one aircraft required something extra special, and it was obvious from the start that it would be expensive. By the late 1960s, several European nations were looking for replacements for existing aircraft. And after 2 years of preliminary discussions, in 1969, Britain, West Germany, and Italy got together to design one. That it would be a 2-seater with variable geometry wings was soon established. But to get the shape right required tens of thousands of hours in different kinds of wind tunnel. The wings would spread right out for high lift at takeoff, be set at intermediate angles for cruising, and folded right back for high-speed penetration of enemy airspace. To get these features right, models were tested in spinning tunnels or at varying angles of attack. They were also fitted with miniature external stores to check that they would separate smoothly. Eventually, by 1972, it was possible to draw a 3-view plan showing what the new multi-role combat aircraft, or MRCA, would look like. At that time, it was secret, and only the designers from the British Aircraft Corporation, later named British Aerospace, Messerschmitt Bulkau Blom, and Air Italia appreciated the fantastic compactness of their creation. It was even smaller than an F-4 Phantom, and a full 20 feet shorter than an F-111, the aircraft the RAF had originally wanted after the cancellation of TSR-2. Of course, Panavia, as the consortium was called, had started work later and could benefit from more advanced technology. Much of their success came from sheer good engineering, not only by the major airframe partners, but by hundreds of subcontractors all over Europe, and in the case of the main radar, in America as well. Everything had eventually to come together and fit together perfectly. Assembly lines were set up at Wharton in England, Manching in Germany, and Turin in Italy. Thousands of parts had to be tested exhaustively to discover, for example, the long-term effects of vibration, or that actuator rods would still work perfectly after hundreds of hours. The landing gear had to open and retract smoothly every time and absorb the weight of the aircraft on touchdown. Even the front of the fuselage and canopy were subjected to tests to determine the effect of bird strikes. Later, the engine intakes would also go through the same treatment. One major test program concerned the crew ejection system. A full-sized mock-up of the cockpit and large one-piece canopy was built into a rocket-propelled sled running on rails. Inside were two Martin Baker Mark 10 ejector seats, on which sat dummies in full flying clothing. Once initiated, the whole ejection sequence had to be both rapid and fully automatic, and in production aircraft can be initiated by either crew member. The canopy flies off first, followed by the two seats whose rockets propel them to a safe height for the parachutes to deploy. This means that Tornado pilots can even eject while taking off or landing. Meanwhile, at Oberndorf in Germany, the famous Mauser company began testing its new Mk 27mm cannon. Most Tornadoes are fitted with two of these, although the RAF's air defense variant only has one. The gun's magazines hold 180 rounds, which can be fired at two different rates, depending on the type of target. The engine selected for the MRCA was the Rolls-Royce RB199, which is built by another consortium of British, German, and Italian companies called Turbo Union. The engine is a three-spool turbofan, developing 16,000 pounds of thrust, yet is tiny in size, only 128 inches long, including the afterburner and target-type thrust reverser to help the aircraft pull up on wet or icy runways. The reverser is a real bonus and something that rival aircraft do not have. During test runs at Manching in 1974, it was found that the engine suffered from surging, so the compressor blades had to be redesigned. Then the turbine disc proved too weak and had to be strengthened. But eventually, the engine was ready for flight testing beneath an RAF Vulcan. There was great political pressure to get the MRCA into the air because of a vindictive campaign to destroy the whole program. But such things can't be rushed, and before the first flight, the engines had run over 2,000 hours on the ground and 320 hours in the air. The first prototype, D9591, was built in Germany and flew from Manching. It was painted bright red and white, and at that time had no weapons, while most of the advanced mission avionics were also absent. The aircraft, piloted by Paul Millett with Niels Meister in the back seat, began taxiing and testing its brakes during the afternoon of August the 14th, 1974. Eventually satisfied, Millett lined up at the end of the runway and, holding the aircraft on its brakes, ran the engines up to full reheat. Then it surged forward, accelerating rapidly to 140 knots when the nose wheel unstuck and finally lifted into the air at 165 knots. From the very beginning, the MRCA handled like a dream. The variable geometry wings, both with and without stores on swiveling pylons, cycled from one extreme to the other with no change in trim. All the test pilots loved it, and soon other prototypes were flying in Germany, Italy, and England. Over the next 5 years, a total of 15 development aircraft were built and flown, and it was christened Tornado. Engine surging still proved a problem, which was only gradually resolved. But the test aircraft were soon flying mission profiles. Here, the CSAS, or Command and Stability Augmentation System, comes into its own. Using CSAS, the pilot's stick and rudder pedal movements are translated into electronic control signals, which are passed to the mechanical actuators physically driving the flying control surfaces. At the heart of the CSAS is one self-monitoring computer to control pitch and a second to control roll and yaw. Pilot demands from the stick and rudder pedals are fed into the appropriate computers and combined with signals from pitch roll and yaw rate gyroscopes to give the correct commands for control surface deflection. The main control surfaces are the rudder, ailerons, and spoilers. Yaw demands result in rudder movement. Pitch demands are reflected in symmetrical movement of the ailerons. Roll demands by differential movements. At low sweep angles, roll demands are also fed to the spoilers. The CSAS system is tolerant of single failures. If multiple faults occur, a direct electrical link is provided to the actuators. In case of total CSAS failure, which might be caused by battle damage, a mechanical backup linkage continues to operate the ailerons, providing a get-you-home safety feature. Wing sweep is most carefully designed, but in the event of failure, the Tornado can be landed with them fully swept back. The fuselage slots have simple but effective elastic seals. About 5% of the wing area disappears into the fuselage at maximum sweep. Since ailerons and spoilers are used as control surfaces, the entire trailing edge is available for powerful double-slotted flaps. Along the whole span of the leading edge are equally powerful slats in 3 sections, augmented by Kruger flaps, which fold down from under the leading edge of the fixed inboard portion of wing. When in the high lift mode, the Tornado wing has the highest lift coefficient in the world. This helps shorten the landing, which is further assisted by large air brakes either side of the fuselage rear.
Morning, gentlemen. This morning we're going to talk about rapid data entry. And we do this.
The men who are going to fly the Tornado all converge on Cottesmore in England for their conversion training. They come from the Royal Air Force itself, from Germany's Luftwaffe and Kriegsmarine, and from Italy's Aeronautica Militare. All pilots and backseaters, called either navigators or weapons system officers, receive the same basic training at the TTTE, the Tri-National Tornado Training Establishment. Here, the aircrew of several nationalities learn how to work together. For example, a German Navy pilot with an English backseater might find themselves flying a Tornado built in Italy. Dedication is total, for flying a Tornado is just about the ultimate goal for many airmen, and their concentration and physical fitness have to be absolute. Each training or operational mission begins in the tight security of the CPGS, the Cassette Preparation Ground Station, which is normally actually underground or in a hardened shelter. Here, an ordinary audio cassette is inserted into a computer linked to a special sensor head. This is placed on an equally special map with very carefully surveyed location coordinates. Each time the button is pressed, the computer records the mission waypoint or target. Additional information on flight paths, headings, weapons load, times, speeds, and fuel states is pre-programmed onto the cassette as well. A hard paper copy is also printed. Then the cassette is loaded into the aircraft's own main navigation computer. Meanwhile, the ground crews will be loading external fuel tanks, bombs, missiles, or other stores. With Tornado, this is not the laborious process it used to be, because sway bracing is automatic. Once these preparations have been made, the crew walk out to their aircraft to begin their pre-flight checks. The weapons system operator programs the weapons load into the digital weapons control system. From then on, the aircraft knows what weapons are on which pylon. The access door is latched firmly secure. At the same time, the pilot walks around making his external checks. Inside the spacious front cockpit, the pilot's tasks are to fly the aircraft, to monitor the aircraft's systems, engage ground targets visually if necessary, and handle air-to-air combat. The weapons system officer, who is also the navigator, first loads the mission profile cassette. His main displays are two screens called tabs, either side of the circular radar and map display. These give control over the mission route plan. They also show the current navigation situation throughout the flight. In addition, they can be formatted for attacks and navigation updates either automatically or manually. The air-to-surface weapons are all controlled from the rear cockpit. Weapons release data is programmed into the control panel while the aircraft is still on the ground. Near the target, pressing a single button will then release the appropriate weapon. No traditional bomb sight is needed. The onboard navigation aids, target sensors, and weapon control systems steer the aircraft and release its bombs or missiles with devastating accuracy. 129 of the 809 aircraft built for the 3 original partner nations are dual control versions for conversion training. They still have the same operational capability as the standard version. As the pilot taxis out, he cannot tell if he is flying a 1- or 2-stick aircraft. Looking through his head-up display, or HUD, he rolls out of the parking area to the runway. As he pushes the throttles forward for full takeoff power, only the weapon control computer can tell him that he may have 10 tons of weapons aboard, more than twice the load of a typical Second World War heavy bomber. The Tornado is a true multi-role combat aircraft. Its designers built into it the capability to carry out 7 basic missions: deep interdiction, counter-air attacks, battlefield air interdiction, close air support of ground forces, reconnaissance, maritime strike, and point interception. All had to be capable of being flown at low level and high speed, at night or in bad weather. These requirements meant from the start that the crew had to learn total reliance on their avionics systems. In flight, Tornado's navigation system is fed from 4 sensors. Their data is optimized in the main computer by Kalman filtering. The primary inertial navigation sensor is in the tail and provides instant information on present heading, attitude, and speed. A secondary system uses Doppler radar to check on attitude and velocity. The air data computer is at the same time monitoring true airspeed and Mach number, so that the pilot always knows his aircraft's exact position, height, speed, and attitude. It all adds together with the weapons control system in the back seat to make it possible for a Tornado to fly straight to its target at about 200 feet and deliver a precision attack without the crew necessarily being able to see anything at all out of the canopy. Actual navigation information is displayed on the right-hand television tab in the rear cockpit. Many kinds of flight data could be called up at the push of a button. In the center of the navigator's view is the all-important combined moving map and radar display. The map can be switched through range scales of 1 million, 500,000, or 250,000. The navigator can then change to a radar-only display. Here, at 10-mile range scale, the resolution will even reveal such features as a line of electricity pylons. Switching to the 4-mile scale produces even more detail, such as the shape of gravel pits or even individual trees. For weapon aiming, the display is keyed into the mission cassette, which was fed in on the ground and has extremely precise waypoints and target designations. The combined map and radar display give incredibly accurate information on where the tornado and its targets are, although the navigator may have to feed in slight adjustments after an hour or so. He uses a simple hand controller for this. The basic interdiction strike versions of the Tornado have a combat radius of 800 to 900 miles, depending on weapons load and atmospheric conditions, which mean they will need in-flight refueling on many missions. The hydraulically retractable probe, which bolts onto the starboard fuselage side, can refill the tanks from a Victor or similar tanker aircraft in about 10 minutes. Alternatively, a hose reel pack can be carried by another Tornado. This method is called buddy refueling and is often done because the tanker Tornado is still fully combat ready. Similarly, while the probe and fairing itself appear large, they do not affect the Tornado's performance or handling in any way. Air refueling is just about the only part of the Tornado's mission which has to be flown by the pilot using his own eyeball skills alone. For almost everything else, he relies on his head-up display, which normally displays symbols in the form of commands. You can see the aircraft symbol in the center, flanked by bars which show where the ground and the horizon are, and the aircraft's attitude in respect of them. Whether flying manually, an exciting and demanding experience at these low levels, or using the autopilot, the HUD tells the pilot exactly where he is at all times. On autopilot, the terrain-following radar and automatic throttle adjustments keep the aircraft just where he wants it, guided by an invisible ski tow riding over the countryside ahead. The computers are constantly checking themselves to help guarantee flight safety. The pilot can select a hard, medium, or soft ride, depending on circumstances. The hard option giving the lowest possible altitude to take advantage of terrain features and avoid enemy radar. This very exaggerated animated diagram shows how the system works. The terrain-following radar's input is digested by the computer, which then adjusts the flying controls to climb the aircraft to avoid an obstacle. Even if the pilot is flying manually, there are built-in safeguards. Once clear, the aircraft automatically drops down again, having been seen on enemy radar for only fractions of a second. As the Tornado approaches its target, the attack is initiated by the navigator. He inputs final data into the weapon control panel, where he has already made his pre-selection, and checks the weapon aiming mode selector. By this time, one of his tab displays is in the attack format. At top left, alongside the letter Y, could be seen the closing range to target. Up front, the pilot knows the target is ahead and can sometimes see it through the HUD. The head-up display shows the predicted bomb fall line together with the target bar at the top and the real target in the distance lined up with it. If visibility is bad, the CCIP, or Continuously Computed Impact Point, will keep the aircraft dead on target. Bomb release is then automatic. The aiming system allows for the weapon's ballistics and also knows the aircraft height, speed, heading, dive angle, and any crosswind. Even inexperienced crews get pinpoint results every time.
Maintain
Returning to base, the Tornado glides in as if on rails, which in an electronic sense it is. It has no braking parachute, unlike most military aircraft. Instead, those air brakes, thrust reversers, flaps, spoilers, and tailerons glue it to the runway before the powerful wheel brakes take effect. If all else fails, the Tornado even has an arrestor hook, although it is definitely not designed for carrier operations. All the Tornado's electronics are built up on a basis of line replaceable units, or LRUs, the good old modular system. This includes the Texas Instruments main radar, which is completely exposed by opening the nose like a door. Most other avionics systems are at convenient eye level along the fuselage. It is the work of only a few moments to take out one module and plug in a replacement. No matter how complex, no calibration is needed after connecting up the new box. Every item has what is known as BITE, or built-in test equipment. BITE tells the flight and ground crews what, if anything, has gone wrong and what needs to be done to correct it. A central maintenance panel displays the status of each item and allows the ground crew to identify any malfunction with confidence using a checklist. An even more extensive system survey can be made by loading a special test program cassette in through the cockpit voice recorder. This feeds into the main computer, and the results can be read off the right-hand tab in the rear cockpit. If anything needs attention, the specialist tradesmen know it will be easy to get at, unlike in some combat aircraft. Over 46% of the Tornado's exterior surface is made up of 430 access panels. Even in the most extreme operational conditions, in desert, Arctic, or jungle, all maintenance is made as easy as possible. If only cars were built like this. In the turnaround between missions, the greatest delay is caused by refueling, although even this takes little time. Fuel is pumped in through a single NATO standard pressure connector at the very high rate of 2,400 pounds a minute. The tanks are filled in order, from front to back, for if the fin tank was filled first, the aircraft might tip up with its nose in the air. The line replaceable unit principle has even been carried as far as the Turbo Union RB199 engines. This, in fact, is common practice in most military aircraft these days. But even so, the diminutive size of the Rolls-Royce design helps the engineers enormously. Changing the entire engine installation is thus simple. On other aircraft, the engines have to be pulled out backwards or the whole tail removed. To change a Tornado's engine, the lower fairing shell of the engine compartment is opened, and after undoing the quick-release connections to the fuselage, the RB199 is lowered by mini-hoists onto a dolly. Even under field conditions, the whole procedure only takes a few minutes. The engine weighs only 2,000 pounds, or less than half as much as that of an F-111. The old engine is wheeled away and its replacement brought up, hoisted into place, and connected up in a similarly short space of time.
Kick the canopy down.
The crews who fly Tornado have enormous confidence, born of the experience that everything works. Their aircraft are normally housed in hardened shelters, and bombing up, fueling, and pre-flight checks are all done under cover. Tornado flight time is fast approaching 1,000,000 hours. That's a lot of experience when you bear in mind the intensity of the workload on each mission. Training flights are normally conducted at a height of 500 feet and are subsonic while over populated areas. In war, the aircraft would be traveling much lower and faster, regardless of weather or visibility. The precision of the terrain following and Doppler radars, coupled with the inertial navigation system, allowed Tornado to approach its target and escape, using every fold in the ground for cover. Even though inexperienced crews can quickly obtain results which a few years ago would have seemed fantastic, that does not alter the fact that to fly Tornado properly, you have to be a highly trained professional. It also takes guts. To attack airfields, you have to fly right down the runway at low level, and the Gulf War showed that that's one way to lose aircraft. The principal weapon used to attack airfields is the Hunting JP-233 cluster dispenser. The rear of each container ejects 30 parachute-retarded bombs, which first penetrate the runway and then explode beneath it. From the front of each container fall 215 small area denial mines to hinder repair operations. Another of Tornado's main missions is to take out enemy radar installations, in particular those controlling surface-to-air missiles. To achieve this, Tornadoes can be fitted with up to 9 air-launched anti-radiation missiles, or alarms. The missiles can even be carried on the side of the wing pylons, in addition to a full bomb load. This British aerospace weapon has only just entered service. It's a complete fire-and-forget system. Its nose houses 4 antennae, which lock on to an enemy radar and guide the missile through a digital processor straight to its target, where an advanced high-explosive warhead with laser proximity fuse does the rest of the work. If the enemy switches off his radar, Alarm will climb and deploy a parachute, then descend slowly to Earth, looking for a target. If nothing else appears, it homes on the last one to switch off. No other anti-radiation missile can do this. Of course, a chaff flare dispenser and active jamming pod are carried on outboard pylons as well. Tornado can also carry all other existing or projected NATO tactical stores, again a unique claim. And delivery accuracy is unrivaled, as has been proven in the United States Strategic Air Command bombing competitions. The German Marineflieger, or Naval Air Arm, has important anti-shipping duties, particularly in the Baltic. Its 2 wings, MFG-1 and 2, operate 100 interdictor strike or IDS Tornadoes, plus 12 dual-control trainers. Their chief anti-ship missile is Cormoran, which was specially developed for the German Navy by Messerschmitt Bulkau Blum. They also make the warhead for Alarm. Cormoran is a large fire-and-forget missile, which has a powerful 352-pound warhead, with a special fuse designed to explode after penetrating up to 3.5 inches of armor plate. On launch, it's propelled by 2 booster rockets for a second before the sustainer takes over. It then descends to about 100 feet and can travel over 20 miles toward its target, guided by both an active radar transmitter and a passive receiver. It's claimed that this system is immune to enemy jamming. Approaching its target, Cormoran descends to a mere 10 feet above the water. It was originally intended that the Luftwaffe, the German Air Force, should be the biggest Tornado user, with nearly 600, but eventually the order fell to 212. Today, these equip 9 Staffel, or squadrons, 2 each with the 4 operational wings and 1 with the training wing. 35 of the German Tornadoes are designated attack leaders and fly in pairs ahead of the main formations, armed with American high-speed anti-radiation missiles, or HARM. Theirs is the Wild Weasel mission, to knock out enemy radars in advance of the following bombers. All the German squadrons fly intensively, as in this mission to penetrate a Norwegian fjord at low level. To the uninitiated, it seems strange to be within a few feet of a hard cliff face one moment, and then a minute later to be 10 miles further on. The pilots have to be constantly alert, scanning their rear-view mirrors as well as watching the forward view through the HUD, but concentrating primarily on their electronic displays, keyboards, and menu buttons. The job is made easier by the comfortable temperature, smooth ride, and low noise level, just the sound of the transonic air rushing past. One of the Luftwaffe's most effective weapon systems is MW1, equivalent to the Royal Air Force's JP-233 cluster munitions dispenser. This was designed by Messerschmitt Bulkau Blom specifically for the Tornado and is a truly formidable weapon. It consists of 4 slab-sided sections with slightly streamlined nose and tail, and inevitably its huge size, as big as a large estate car, exerts considerable drag. MW1 is a gigantic box of firepower, containing 112 double-ended tubes firing sideways. Each tube has a diameter of nearly 6 inches and fires munitions left and right simultaneously to cancel out recoil. Munitions include the KB-44 shaped charge bomblet to attack tanks from overhead, MIFF, an anti-tank mine with a passive sensor which responds to engine noise, MUSA, a parachute-retarded fragmentation mine for use against soft targets, MUSPA, an area denial fragmentation mine with a delayed action fuse designed to be strewn along enemy runways, STABO, a large parachute-retarded runway cratering bomb, ASW, a rocket-propelled weapon designed to penetrate hardened aircraft shelters. MW1 is loaded with whichever weapon or combination of weapons is most suitable for the intended target. The system is particularly effective against large formations of enemy tanks and troops, or against airfields. A single high-speed pass has devastating effect, even seen in slow motion. The number of munitions carried varies according to type, from 224 of the large Stabo to an incredible 4,700 KB-44s. Similarly, by making their attack at different heights, the crew can scatter a wide or compact area of ground. After a mission, the empty MW1 containers are jettisoned, leaving the aircraft clean to make a supersonic escape. Italy's Aeronautica Militare is quite small, so the multi-role concept was particularly attractive. They have 100 IDS Tornadoes, of which 12 are dual-control conversion trainers. These are assigned to 3 Gruppi, the 154th, 155th, and 156th, which respectively form part of the 6th, 50th, and 36th Stormy, or Wings. The golden lightning flash on the tail identifies aircraft of the 156th Gruppo, based at Gioia del Colle in southern Italy, between Bari and Taranto. This unit has an anti-shipping commitment. The Tornado has allowed the Italian Air Force to dispense with specialized reconnaissance squadrons, and it is often flown with Messerschmitt Bulkau-Blum camera pods. In fact, the Italian Tornadoes are almost identical to the German ones in avionics and weapons. Because of Italy's strategic situation in the Mediterranean, the maritime strike role is particularly important, and Aeronautica Militare Tornadoes carry the Cormoran missile in addition to American 500-pound and 1,000-pound bombs. They can also carry British BL-755 cluster bombs, the MW-1 system, Maverick anti-tank missiles, and nuclear weapons. As on the German aircraft, the electronic jammer pod can be Cerberus, carried on the left wing, although an alternative is the homegrown Elettronica EL-73. Increasingly, the Italian aircraft have also been fitted with the bolt-on flight refueling probe and use the American Sergeant Fletcher buddy pod to pass fuel to each other. Watching tornadoes land is quite educational and always fascinating. The fantastic array of flaps, slats, spoilers, and air brakes generates so much lift on the final approach that it's quite incredible, as is the aircraft's ability to pull up on the ground in such a short space. Kept secret for some time, even from Britain's partners in Panavia, was the Royal Air Force's requirement for an all-weather interceptor, or as it has become known, Air Defense Variant, the ADV. The first prototype, known then as the Tornado F-2, rolled out from Wharton for its maiden flight on the 27th of October, 1979. It would not enter production for another 5 years, because despite superficial appearances, it is really a different airplane inside a similar package. It's actually more than 4 feet longer than the IDS version, for 3 reasons. First was the need for a longer and more pointed nose radome for the Marconi Foxhunter radar. Second was the need to provide extra space under the fuselage for 2 tandem pairs of 12 feet long Skyflash missiles. And third, after the 18th production aircraft, was the incorporation of a new variant of the RB199 engine with extended afterburners. Bonuses from all these modifications were improved supersonic performance and the ability to carry 200 extra gallons of fuel. Even so, maximum endurance without in-flight refueling is only about 2 hours. So the definitive Tornado F-3 is fitted with a permanent, fully retractable refueling probe. It's built into the port side of the fuselage instead of being bolted onto the starboard. And, to make room for it, one of the Mauser 27mm cannon has been removed. This is no problem, because the F-3 expects to rid the sky of enemies before getting within gun range. But it's nice to know the gun, seen here in slow motion, is there for emergencies. As an ADV lands back at Wharton, you can see the wings fully extended to a full 67 degrees, thanks to a modified wing glove, and also the lack of Kruger flaps. Less obvious is the fact that the tailerons have been modified to clear the thrust reversers, which had to be repositioned because of the enlarged afterburner and new tail profile. Like the old Lightning, the ADV is designed as an interceptor, so standby crews learn to run at the scramble alarm. The Royal Air Force now has 165 Tornado F-3s, while a further 24 have been built for Saudi Arabia. Main armament is the 4 Skyflash missiles under the fuselage, but short-range Sidewinders are also carried. The Skyflash is guided by a monopulse radar seeker and was developed from the earlier American Sparrow. It has a range of 31 miles and can be launched from as low as 100 feet. The older Sidewinder has an infrared seeker head and an effective range of some 9 miles. The Foxhunter radar in the aircraft's nose allows the aircraft to track and engage targets flying at extreme altitude or right down on the deck. The ADV is the most advanced interceptor the Royal Air Force has ever possessed. It can also be used in the attack role, carrying the same sort of 10-ton payload as the IDS, but its radar, avionics, cockpit displays, and above all, computer software are optimized for the air-to-air mission. It's not really a dogfighter, though, such as the American F-16 Fighting Falcon, for example. It's designed for the air defense of the United Kingdom, which means bringing the battle to the enemy as far from the shore as possible. As one pilot put it, it's supposed to engage hostile aircraft 400 miles out to sea on a dark and dirty night, with lots of targets at low level and heavy electronic countermeasures. The pilot would not find his cockpit much different from that of an IDS, but in the back seat, it's not the same story. The arrangement of the tabs is side by side, and they have different tasks beyond that of navigation. The F-3 relies heavily on its Foxhunter radar in the nose, which could detect targets at very long range, continue to search for new targets while tracking others, and carry on operating in the face of severe jamming. Radar data is provided on the tabs in a variety of formats, such as target detection or target tracking with details of speed, height, and heading all flashed up for the operator. Foxhunter also gives high-quality ground mapping to update the navigation system. The big Skyflash missiles, which may in due course be replaced by the American AMRAAM, or Advanced Medium-Range Air-to-Air Missile, are forcibly ejected by Fraser-Nash cartridge-powered rams to ensure clean separation. The advantage of the more expensive newcomer is that it is fire and forget, whereas Skyflash has to be monitored all the way to its target. When you see the Tornado F-3 at home in its element, flying nothing less than an aerial ballet, it's easy to forget that it's a deadly fighting machine. An aircraft which has proved through exhaustive tests that probably better than any aircraft known, it can intercept and destroy enemy aircraft and cruise missiles, and that includes under conditions of the most intense electronic warfare interference, including high-power jamming and the release of chaff or flares. It really has everything, including 2 reliable high-performance engines which give its crews confidence way out over the ocean on maritime missions. Handling is carefree and endurance greater than any other air defense fighter in the world. But of course, it's not just the airplane which makes the Tornado a weapon system about which so much can be said. Its highly skilled and professional crews deserve a round of applause as well. The F-3 seems to float rather than fly as it approaches its VC-10 tanker in a display of elegance which might be rivaled but not surpassed. Such flexibility allows the fighter to defend an enormous volume of airspace, from Iceland to the Baltic. One feature of the F-3 not yet mentioned is JTIGS, the Joint Tactical Information Distribution System. This is a new secure data link system for passing information rapidly from ground stations to aircraft, giving the Tornado backseaters instant access to the whereabouts of every aircraft in the vicinity and showing whether it is hostile or friendly. The information is presented on one of the two tabs. If this system works out, it will give the Tornado ADV even more versatility than it already possesses. But goodbye ADV and hello ECR. This electronic combat and reconnaissance variant is the latest Tornado and has been developed for the Luftwaffe. The Italians are also keen, and there's even the possibility that it might be chosen as the future Wild Weasel aircraft for the United States Air Force, although no one is placing any bets. The most surprising thing is that so far, none have been spoken for by the RAF, which badly needs such an aircraft. Although it can still fly a normal attack mission, the ECR has no guns. Its main mission is to find, pinpoint, and destroy enemy air defense systems. It can also fly standoff reconnaissance and border patrol, advanced real-time reconnaissance, and give electronic support to friendly aircraft. Other Tornadoes can also fulfill an airborne command and control role in a limited way, but this is something really new. The aircraft contains an emitter location system, which detects radars, determines whether they are hostile, compares them with a threat library built into the computer, and lists them in order of priority. The most dangerous, such as a surface-to-air missile guidance radar, is immediately jammed. Simultaneously, an imaginary aircraft is generated a safe distance away from the real aircraft to mislead the enemy missiles. How this apparent miracle is achieved is naturally very much top secret. The ECR can also carry infrared equipment, anti-radiation missiles, and special data links. The Tornado first saw combat during the Gulf War to free Kuwait from Iraqi occupation in January to March 1991. Here, RAF and Saudi Tornadoes joined together in perilous attacks on enemy air bases in the center and north of Iraq. They were painted in desert camouflage, and along with the rest of the Allied air forces, accomplished their task remarkably quickly. Unfortunately, and largely through simple bad luck, 5 Tornadoes were lost. The principal weapon system deployed was the JP-233 cluster dispenser seen earlier. As this was a real war, the Tornadoes flew most of their missions at what one pilot called the lowest possible height. It's not, however, advisable to use JP-233 at less than 200 feet to avoid damaging one's own aircraft. This was real nap-of-the-earth flying. The Tornado's sophisticated terrain following and navigation radars allowing them to hug the wadis and avoid Iraqi radars which had not already been destroyed during earlier Wild Weasel missions. Subsequently, the Tornadoes knocked out many hardened aircraft shelters. On many of the longer missions, in-flight refueling was essential, and old Victor tankers yet again proved their worth. Once part of Britain's frontline bomber force, the Victors were not the only oldies but goldies in the Gulf. By the end of January, targets included large bridges over the rivers Tigris and Euphrates. This was a job for smart laser-guided bombs, and buccaneers were sent out to provide active laser designation. The RAF's GR-1 and many other Tornadoes have a laser ranger and marked target seeker in a small chisel window fairing under the nose. It cannot send out a laser beam, as can the American AVQ-23E pave spike pod carried underneath a Buccaneer. The collaboration between old and new showed the world what precision aiming really means. The laser-guided bombs destroyed each of their targets with an accuracy worthy of the dam busters. And of course, one Tornado squadron is 617. It's possible, especially since the Buccaneer is running out of air life, that a later mark of Tornado, designated GR-4, will carry an active laser designator and ranger to replace the existing equipment. Until that time comes along, though, the Tornado is still doing a fine job and proving that the multiple role concept really does work. In fact, during the Gulf War, you might say that if Saddam Hussein sowed the whirlwind, he reaped the tornado.